Hello everyone, I'm Anisohana here. So in this part of chapter, I will explain more about underdetermination and also its example.
Definition of underdetermination divided by three forms, which are by general, meaning that the stage in science where we do not have enough or sufficient evidence to make proving. And the second one is theory by scientific, simple idea that the evidence available to us at a given time may be insufficient to determine what beliefs we should hold in to respond it. And the last one is theory by evidence. A unique theory is never detected by the evidence, not even if it had all the possible evidence. The scientists cannot tell if their story is true, but they can only tell if it is false. Next, we move on to example of underdetermination. For example, someone spent 10 ringgit to buy orange and apple. One orange costs 2 ringgit and one apple costs 1 ringgit. So, one would not have enough evidence to know what the combination of orange and apple was purchased, whether 4 orange and 1 apple or 3 orange and 2 apples. So, one would say that belief in what combination was purchased is undetermined by the available evidence. Okay, let me explain again. If all I know is that you spent 10 ringgit on apples and orange, and that apple costs 1 ringgit, while orange costs 2 ringgit, then I know that you did not buy 6 orange, but I do not know whether you bought 1 orange and 8 apples, 2 orange and 6 apples, and so on. A simple scientific example can be found in the rationale behind the sensible methodological adage that correlation does not imply causation. Next, example 2 of underdetermination. The correlation between kids who loves to play games and antisocial kids. Statement 1. Kids that play games are antisocial. Statement 2. Kids that are antisocial loves to play games. Both statements may be true or may be false, since there might be another factor that affect each other, such as neglect of parents.
Hi, I'm Fatina Zribitinoudin, and now I will explain to you the first topic in underdetermination, which is holistic underdetermination. Let's get started. In science, holistic underdetermination considers that it is normally impossible to test scientific hypotheses by themselves, but only in conjunction with other hypotheses. What is holistic underdetermination? It arises whenever our inability to test hypotheses in isolation leaves us underdetermined in our response to a failed prediction or some other piece of disconfirming evidence. In other words, if our prediction fails, we cannot validly conclude that the hypotheses are incorrect. This is because hypotheses have empirical consequences only when conjoined with other hypotheses and beliefs about the world. A failed prediction or falsified empirical consequence typically leaves open to us the possibility of blaming and abandoning one of these beliefs and auxiliary hypotheses rather than the hypothesis we set out to test in the first place. We can also say that theories or hypotheses can only be empirically tested in groups or collections. We can only understand one current hypothesis in relation to background beliefs about the world and other hypotheses. In holistic underdetermination, there is a term that is important for us to know, which is falsifiable. Falsifiable is able to be shown or demonstrated to be false experiment. For example, the claim that God exists is not falsifiable. Therefore, it is not scientific theory. Karl Popper stated that what distinguishes scientific theory from non-scientific theory is falsifiability. A theory is scientific if and only if it is falsifiable. Let's take a look at how to take any hypothesis and demonstrate it false. First, the physicists who will create and make the theory and prediction about the experiment. Then, they will do the experiment. After they do the experiment, if the prediction is not obtained from the theory and prediction, then it will consider that the theory is false. Hence, the theory is called falsifiable. This is the example about what is meant by falsifiable under holistic underdetermination. Newton's scalar mechanism is the example of holistic underdetermination. It is a theory about the motion of the planet. It has happened when Newton's scalar mechanism failed to correctly predict the orbit of Uranus, and the scientists at that time did not abandon the theory but protect it by challenging the background assumption that the solar system contained only 7 planets. This strategy bore fruit where it proved that the falsity of Newton's theory by calculating the location of a hypothetical 8th planet influencing the orbit of Uranus, where the astronomers Adam and Leverrier discovered Neptune in 1846. But the very same strategy failed when used to explain the existence of Vulcan in Mercury orbit. Vulcan is an additional planet located between Mercury and the Sun, and this phenomenon would receive satisfactory explanation until the arrival of Einstein's theory of general relativity.
Let's take a look more carefully. So, we'll represent the theory as true with T. If the theory is true, then the experiment will produce result P. T implies P, basically. The experiment did not produce result P, not P. Therefore, the theory is not true. This seems to be just a classic use of modus tollens. But I think there's something a little bit deeper going on here. Let's look at it logically. The theory is true. Assumed indirect proof. Premise 2, T implies P, from our other scientific theories and understandings of the ways experiments work. T implies P. It's not the case that P. We discover this through experiment. Therefore, it's not the case that T, 3 for modus tollens, T and not T, 1 for conjunction. Therefore, using our indirect proof, 1 through 5, we can conclude not T. The problem here is that it seems that not T is not our only possible conclusion. We could instead deny premise 2 and say it's not the case that T implies P, basically saying that our other scientific theories are less important, or there's some one specific scientific theory in there that we can throw out and hold on to T because we like T better. It seems that the information we have right now underdetermines which conclusion we should draw. We don't know if we should draw conclusion premise 6 or premise 6 star. Either of them are viable because we've assumed both that T is true and that our other scientific theories are true and that T implies P. But there's no way for us to tell which of those assumptions we should throw out because we've now reached a contradiction. Let's put this into a more specific context and talk about Newton's celestial mechanics. So, Newton's celestial mechanics is a theory about the motion of the planets. We're going to take that as our T, our theory. If Newton's celestial mechanics is correct, then the orbits of the planets will be correctly predicted. T implies P. Newton's celestial mechanics does not correctly predict the advance of the perihelion in Mercury's orbit, not P. Therefore, Newton's celestial mechanics is false. Once again, this seems to be a classical standard use of modus tollens. The problem is that we could also come up with another conclusion. Therefore, there exists another planet, Vulcan, closer to the Sun that is affecting Mercury's orbit. And in fact, that was the conclusion that was drawn by many scientists at the time. Instead of denying the original theory, they denied one of their assumptions or one of their other theories that caused them to reach the conclusion that T implies P. They said that it's possible for Newton's celestial mechanics to be correct, but that it not predict the orbit of the planets correctly. Why? Because we don't have the right information about what planets exist. Basically, the evidence that we have underdetermines the conclusion. All that has been shown is that one of the theories that we accept is incorrect. But since we can't test one without all of the others, there's no way to tell which theory is incorrect.
Assalamualaikum, my name is Nur Shamimi Bentinani, so let's move to the contrastive underdetermination. The definition of contrastive underdetermination is the ability of the evidence to confirm any given hypothesis against alternative, and the central focus of discussion in this connection, which is equally often regarded as the problem of underdetermination. It concerns the character of the supposed alternative. In a simple word, contrastive underdetermination is about take a set of evidence and shows that more than one theory can support that evidence. You already know about the contrastive underdetermination, which is many theories that can support one evidence. Okay, so from this picture, there is a 5-point which is D1, D2, D3, D4 and D5. So there are many stories that can fit the data. For example, you can see the blue line, the red lines and also the green lines. So in order to connect all this data, you can use all this theory. So it is an infinite number of theories can be run through this data. So the general idea is that evidence we have can be used to support any numbers or theories so long as those theories account for all the evidence we have. Another example for the contrastive underdetermination, we have number 2, number 4, number 8 and unknown number at the last. So in order to get the unknown number, we have a lots of theory. For example, in this picture, I stated 3 theories. Okay, so first theory is that 2 times with 2 we get 4, 4 times 2 we get 8 and 8 times 2 we get 16. Yeah, so to make sure that it is a true value, so we need to use another theory. For example, we need to add by its own number. For example, 2 plus 2 is equal to 4, 4 plus 4 is equal to 8 and 8 plus 8 is equal to 16. So the next theory is a backward theory. For example, from the unknown value to get the number 2. To make sure that we need to divide by 2. What numbers if divide by 2 will get 8? It's 16. So 16 divide by 2 will get 8. 8 divide by 2 will get 4. And lastly, 4 divide by 2 will get 2. So meaning that for this contrastive underdetermination, a many theory that can support one evidence. So it is stated here.
In this video, we're going to be talking about contrastive underdetermination, which takes a set of evidence and shows that one theory is not the only theory that can be supported by it, that more than one theory can in some way be supported by it. To get a sense of this, let's look at a little bit of a simplification of the idea, but hopefully it'll give you an intuition to what the problem is here. So imagine you have, let's say, 3 data points on a graph, and you want to come up with a theory to predict where other data points are going to show up. You could come up with this theory, which would be supported by all the data points on the graph. However, you could also come up with this theory, or this one. Any number of different theories or functions or lines can be run through these different data points. And in fact, there's an infinite number. And while you might think that adding more data points and doing more research might limit some of these, no matter how many data points you add, there's still going to be an infinite number of possible lines or theories that can be drawn through them. Basically, for any data set, there are an infinite number of possible lines that describe it. So, for any body of evidence, there are an infinite number of theories that can describe it. Like I said, this is a bit of an oversimplification of the idea, but hopefully you get a little bit of the intuition. The idea is that the evidence we have can be used to support any number of theories so long as those theories account for all the evidence we have.
Hi, my name is Nur Aina Syaraskina binti Muhammad Syahrudin. Now we are going to continue to talk about the transient underdetermination.
Firstly, what is the transient underdetermination? It is theories that are not compatible by the mean of experience and observations. In generally, it is theories that are not empirically equivalent, yet they are actually well confirmed by the evidence. Basically, it is a temporary even if we do not come up with them. Such options have historically turned out. Every previous theory has been shown to be incorrect, even though we could not think of those other theoretical equivalence alternatives that we now accept.
There are many theories we have learned until now, but are our theories correct? A theory is transiently underdetermined if and only if it is one of the rival theories which makes different claims about unobservables but are well suited with all the evidence available at a point of time in the development of science. Theories cannot be shown to make correct predictions, currently well confirmed by the data and evidence, but will not always be. Something might change or happen that cause the theories to go into different directions. Non-empirically equivalent theories that are equally supported by the data have always been revealed, and it is the selfish bias to claim that we are sure we have it right this time. Note that you may break the tie between the rival theories in such underdetermination. As for the example, humans need to drink water in order to survive. However, there is another claim that if there is no water, you can use other elements such as foods that can substitute to water for survival. Now, let's talk about the scientists who had different theories on the particular issues. First, Sir Isaac Newton. He was born at 4 January 1643. He was a mathematician, physicist, astronomer, theologian, and author. He had proposed many kinds of laws, which one of them is Newton's law of motions. You know what the second scientist is? Albert Einstein. He was born on 14 March 1879. He was a German-born theoretical physicist, which is one of the greatest physicists of all time. He also had proposed many kinds of law, which one of them is Albert Einstein's relativity. Now, we're gonna look at a little bit about these two theories on the particular issues. Firstly, indetermination of GPS location according to Newton's law. GPS uses 4 satellites that are in view of the receiver to solve 4 equations for the x, y, z coordinate of the receiver and A value, D value, which is the difference in time between the receiver's clock and the satellite's clocks. The equations that are solved to approximate a receiver location using GPS such as below, which is a little bit simple equation with just a few factors that are needed to be considered. However, the things are not easier. There are a few things that Newton did not know. He didn't know that gravity slows down the time. Secondly, clocks near the surface of Earth run slightly slower than clocks higher up. This effect must be accounted for by GPS satellites, which rely on accurate time measurement to calculate their position. However, this method has included in Einstein's theory of relativity. He has explained many of the things that Newtonian mechanics cannot explain. Albert Einstein's prediction of the theory of relativity have confirmed by experiments such as GPS. Factors that is needed in determining the GPS location such as the speed of light, the equivalence principle, the Sennett effect, time dilation, gravitational frequency shift, and relativity of synchronization. Next, the issue on the Mercury orbit. The orbit that is closest to the Sun, called the perihelion. We observe that as Mercury orbits the Sun, the perihelion advances by a small amount. However, Newton's theory does not fully explain this precession of Mercury's perihelion. There is about 43 arc-second per century discrepancy between the Newtonian prediction and the observed precession. Meanwhile, according to Albert Einstein's general theory of relativity, he had provided a full explanation for the observed precession of Mercury's perihelion without the need for an extra planet. According to this theory, Mercury's orbit perihelion shift forward twice to Newton's theory. As Mercury moved toward its perihelion, it moved deeper into the Sun's gravity well. Its motion into this region of greater curvature of space-time causes the perihelion to advance. Einstein's theory of general relativity predicts exactly the amount of perihelion advance seen in Mercury. Einstein views this result as the most critical test of his theory to date. Next, we're going to talk about the black hole. Black holes obey all laws of physics, including the laws of gravity. Black hole is explained through Newton's law of gravitation at first. By using this principle, John Michael called this object as dark stars due to the gravitational pull of the body that may be so strong that even light cannot escape from their surface and reach to our eyes. However, today we have learned that nothing can travel faster than the speed of light. Later, it was concluded that there is no such dark star or black hole obtained while using this theory. This is because even though the light and other objects may not be able to fly out on their own from such dark stars, but they can still be extracted out by applying a suitable force. The situation changed with the word of Einstein. In this theory, the effects of gravity are incorporated by making space and time curved rather than flat. The behavior of matter in general relativity is given by a natural extension to curved space-time of the behavior one had in flat space-time. In this theory, the curvature of space-time can be made such that we get a trapping region, such as we can get a black hole. Also, we can get there is a boundary surface called the horizon.
Welcome back to Carneades.org. Today we are going to be looking at the final video in our series, A Theory is Just a Theory, Underdetermination in Scientific Theory. In this video, we're going to be looking at the question, are our theories correct? And talking about the problem of transient underdetermination. Now, we didn't really talk about transient underdetermination in the first video because it's a type of contrastive underdetermination that we talked about in the last video. However, the contrastive underdetermination problem we talked about in the last video was only dealing with empirically equivalent theories. Basically, theories that are and will always be equally well confirmed by a data set. However, non-empirically equivalent theories are theories that are currently equally well confirmed by the data and by the evidence, but won't always be. That there is something out there that might change or might happen that would cause the theories to go in different directions. And yet they're still both equally well confirmed by the evidence that we have. So something is transiently underdetermined when you have two different theories that make different predictions about the future, but are equally well supported by our current evidence. So, the problem here is that even if we don't conceive of them, such options have historically always turned up. Every single previous theory that we have has been shown to be incorrect, even though we could not conceive of those non-empirically equivalent alternatives that we now accept. I've done a number of other videos on kind of this concept, though I haven't called it transient underdetermination by name, so I'm not going to spend too much time on it. It seems to me pretty straightforward, and I'll leave you here with a quote from Stanford. So, in the past, we have repeatedly failed to exhaust the space of fundamentally distinct theoretical possibilities that were well confirmed by the existing evidence, and we have every reason to believe that we are probably failing to exhaust the space of such alternatives that are well confirmed by the evidence we have at present. So, to sum up everything we've talked about in this video series, we've shown that no theory is falsifiable. We can always call into doubt either the theory under scrutiny or our other theories, or our ampliative principles in the face of contradictory evidence. Science as a method is irrational. There's no rational way to decide how to revise our theories in the face of contradictory evidence. And in fact, no theory can be shown to be true, or flat out true. No evidence can decide between empirically equivalent theories. And in fact, no amount of evidence can even show that one theory is more likely than the other between empirically equivalent theories. There's no rational way to choose. The only way you can choose is through your own personal psychological biases or by flipping a coin. And finally, theories can't be shown to make correct predictions because theories that are non-empirically equivalent but equally well supported by the evidence that make different predictions have no way of being distinguished or shown to be more or less correct than our current theories until we reach such a point that the predictions are shown to be true or false, and even then we can call into question our previous beliefs about science and our previous theories. Non-empirically equivalent theories that are equally supported by the data have always emerged, and it's just selfish bias to claim that we are sure we have it right this time, in this very short amount of time. The only reason perhaps that you think that is the psychological fact that you won't be around to see far enough into the future where things will have so drastically changed that maybe in fact all the theories that you take as true right now have been shown to be false. So, to sum it up, no theory can be proven to be false. No theory can be proven to be true. The methods to create theories are irrational. And we cannot show that theories will continue to make correct predictions. Theories might be useful to do things, but in the end, a theory is just a theory. Watch this video and more here at carneades.org, and stay skeptical, everybody.
As the conclusion for this chapter, we can use theories since it might be useful to help in solving the problems. However, the information obtained does not determine what conclusion we can draw from it.
Hi, we meet again. I'm Anis Sohana here. So in this part, I will explain more about definition of observation. So let's go. Definition of observation, meaning that an act or instant of noticing, perceiving, or watching. Observation also the habit of observing or noticing. Besides, the information or record secured by such an act. And the last one, observation, is fundamental aspects of all scientific research. Scientists learn and envelop concepts through observing the environment, people, animals, things, and how they affect each other. In a short, an observation is something that you have learned by saying or watching something and thinking about it. Observation can be divided into two. The first one is qualitative observation, meaning that research process of using subjective methodologies to gather information or data. Since the focus on qualitative observation is to equate quality differences, it is a lot more time-consuming than quantitative observation. Let's say you are observing the leaf of a plant and you write down these observations. The leaf is yellow-green in color, has spiky edges, a waxy surface, is very large and smells bitter. This type of observation is what we call a qualitative observation. Another example is 5 major sensory organs and their functioning. For example, sight, smell, touch, taste, and hearing. So this doesn't involve any measurements or numbers, but instead characteristics. Another type of observation is quantitative observation. Quantitative observation is an objective collection of data which is primarily focused on numbers and values. Results of quantitative observation are derived using statistical and numerical analysis methods. This observation technique is conducted on a sample which best represents the target market. Because it is important to have a larger sample size so that the observations can be made considering most of the diversities. Okay, by considering a large population, the observation results are most likely to have higher credibility. Once a market researcher collects data from the sample, the process of analysis begins and observed results are attained.
So now we will move to the type of observation. Observation is very important part of science. It led us to see the results of an experiment even when the result that we get is not a result that we expect. The first observation is quantitative observation. It is an objective collection of data which is primarily focused on numbers and values. The results for this quantitative observation are derived using a statistical and numerical analysis method. Now, let's take a look about the advantages of this quantitative observation. So, it is about the accurate result. The data that can be measured from this quantitative observation will produce an accurate result. The second one is the collect information will be very quickly. This is because we just focus on the numerical value. The third one is constant result. With this quantitative observation, we will gain the constant results. For example, the boiling point of water at sea level will be 100 degrees Celsius and this will not change with other variables that remaining constant. The next one is focus on the numerical values only. This quantitative observation just need to focus for the numericals and statistical values. The last one is quantifiable data. This quantitative observation very suitable for statistical investigation. Some example of quantitative observation. The first is volume. For example, the volume of the EDTA solution that need to pour in that beaker is about 215 milliliter. The next is weight. For example, Ali's weight is 43 kilograms and then Abu's weight is 52 kilograms. The third one is amount of money. For example, the amount of money that I got during Hari Raya is only RM15. The next is number of people. The number of people that allowed in that house is not more than 15%. And the last one is age. For example, my age is 22 years old. Qualitative observation is a research process of using subjective methodologies to gather information or data. Basically, for making a qualitative observation, we need to use all our 5 senses. Our nose to smell, mouth to taste, our fingers to touch, our ears to hear, and lastly, eyes to see. So now let's move to the how to make a qualitative observation. From this given picture, which is orange and its leaf, we can do a qualitative observation. First, we can see a yellow-green in color and a spiky edges for that orange leaf. So using our fingers, we can touch the leaf of the orange and we can feel it is a waxy surface. By using our eyes, we also can see the leaf is large. And lastly, with our nose, we can smell the orange leaf. For example, the smell is bitter. Then, the most important thing in qualitative observation is it do not contain any measurement or numerical value. Okay, now let's look at this picture. And can you determine which is a qualitative observation and which is the quantitative observation? Yeah, it's true. All of this picture is a qualitative observation because it do not contain any numerical value because we do the observation from this picture by using our 5 senses. Okay, now we already learned about the qualitative observation, quantitative observation. So let's see the example for these two quantitative and qualitative observation. So example 1 is I have 2 brothers and 3 sisters, and the second example is the t-shirts are color blue, black and red. Okay, so from this example we can determine which is the qualitative and which is the quantitative. So the data sample in example 1 is quantitative observation because it is contains a numerical values, and the data sample in example 2 is a qualitative observation because we make an observation by using our 5 senses. Okay, so the differences between qualitative and quantitative observation, basically, quantitative observation deals with the data that can be counted, while the qualitative observation deals with the data that can be described in terms of the 5 sensory organs.
Hi everyone! In this video, we're going to be talking about qualitative and quantitative observations. So what do we already know? We know that observation is using our senses and tools to record data about an object or event. Let's do a little observation practice with these puppies. If you want, you can pause the video to think of your observation. Something I observe is that each puppy has 2 eyes. So now that we're warmed up, let's begin to talk about qualitative observations. The word qualitative comes from the word quality, which means a trait of something. A qualitative observation is when we use our senses to observe. So let's go back to these puppies and try some qualitative observations. We're going to pretend to use our sense of hearing and touch, as well as our sight. I can see the puppies are small. I can hear the puppies barking. I can feel their soft fur. Now, for quantitative observations. The word quantitative comes from the word quantity, which means a measurement of items. A quantitative observation is when we use measurements to observe. Now back to our puppies. Let's make some quantitative observations. There are 5 puppies. Each puppy has 2 eyes. If we were actually with these puppies, we could measure their height and weight. Those would also be quantitative observations. So now that we've learned about qualitative and quantitative observations, let's review. See if you can fill in the blanks. What is a qualitative observation? It's an observation made by using our senses. what is a quantitative observation? It's an observation made with measurements. Now to end this video, let's practice. If you want, you can take out a piece of paper. We're going to imagine that we're on this beach. You can hear the ocean, touch the sand, smell the salt water. I want you to make 3 qualitative observations and 3 quantitative observations. You can pause the video until you're finished. And with that, we're done. Qualitative and quantitative observations are very important to our science toolbox, and you can practice these skills at home. Thank you for listening, and if you have any questions, let me know.
Hi, it's me again, Fatin, and for this chapter, I will explain to you guys about the importance of observation along with the role and its advantages, also disadvantages. Why observation is important? First, it let us see the result of an experiment even if they are not the result that we expect. The second one, it let us see unexpected things around us that might stimulate our curiosity that will lead to a new experiment. And lastly, observation is an accurate observation. This is because our eyes and brains usually play tricks on us, letting us see what we expect to see instead of what is actually there. The role of observation. Observation is essential in science. Scientists use observation to collect and record data, which enables them to construct and then test hypotheses and theories. In order to proceed in doing any investigation or research, observation needs to be done. In this process, they will have to collect and record the data. Next, it is also used to test predictions on experiments. By observation, we can also predict the result of an experiment. Then, scientists observe in many ways, which is with their own sensors or tools such as microscopes, scanners, or transmitters to extend their vision or hearing. These tools allow for more precise and accurate observation. And lastly, observational data usually consists of detailed information about particular groups or situations. Advantages of observation. First, it is a very direct method for collecting data or information. Then, the data collected is very accurate in nature and also reliable. It also can improve the precision of the research result. Next, the problem of depending on respondents is decreased. It also can help in understanding the verbal response more efficiently. It also can be made continuously by using good and modern gadgets. And lastly, observation is less depending in nature. Let's take a look at the disadvantages of observation. First, the problem of the past cannot be studied by means of observation. Then, it having no other option. One must depend on the document available. Then, some instruments in doing the observation are costly. The next one is, one cannot study opinions by this means. Sampling also cannot be brought into use, and observation involves a lot of time, and lastly, a complete answer cannot be obtained by observation alone.
Now, let's move to a method of making observation. Okay, so we need to use our own 5 senses, which is nose, finger, mouth, ear, and eyes to making a qualitative observation. The next is we will use an equipment with help of a machine. For example, we will use a microscope to observe very tiny organisms that cannot be seen with our naked eyes. The second is burette. For example, we need to do a titration, so the EDTA solution will be placed on the burette. The next one is binoculars. Binoculars is to see the far object. And lastly, petri dish. Petri dish is a small dish in which organism can be placed for the observation.
Next, we are gonna talk a little bit about theory. what is the theory? A theory is a rational type of abstract thinking about a phenomenon or the results of such thinking. Secondly, theories may either be scientific or other than scientific. Meanwhile, scientific theory is a well-confirmed type of explanation of nature that have made in a way consistent with scientific method and fulfilling the criteria required by the modern science. Now, let us take a look at the relationship between observation and theory. All scientific knowledge must be based on the observation as the basis of scientific method, but there is close link between observation and theory. Knowledge is a prerequisite for making scientific observations. According to Caso, all observation in science is influenced by theory. Next, term theoretical cannot distinguish an idea as being believable or not. They all describe objects or events that are not directly observable. It is crucial to see how theory influences observation. With a theoretical background, it's a start to describing the method. Also, it allows the different interpretation on how one will specify the outcome and conclusions. After the interpretation, as the theories are things that cannot be directly checked by the observation, it can be regarded as a useful model. Now, let us take a look at the example, the relationship of the observation and the theory. First, it is a theoretical understanding of the world guides of our selection of what observation to do. Secondly, it can guide in the decision as to when the observations are credible. Third, theories guided the description of the observations to be irrelevant. And next, describing what is observed has a significant theoretical influence.
The last part for this chapter is theory influences observation in several ways. The first one is theoretical understanding of the world guides our selection of what observation to do. To collect data must be directed by theories that tell us where to look and what is important enough to warrant attention. Meaning that in order for us to collect information, we must guide it by theories that will tell us where to find that information and it needs enough consideration and attention. For example, gravitational acceleration. The next one is guiding decision as to when observations are credible. Make sure that there are no distorting factors and correcting any factors that persist. Number 2, this role of theory is clear in cases of observation that are assisted by machine. For example, the using of telescope. In this part, we have to ensure that there are no any causes or incident that will affect the theory itself. This kind of theory mainly facilitated by machine. The third one is theory guides the description of observation. We have to use accounting theories to help clarify what observation means and guide the appropriate description of the observation. Number 4, describing what is observed has a significant theoretical influence. Number 1, in the case when no apparatus assists the observation. Number 2, grouping the individual item we encounter under heading of the same kind of thing, meaning that we categorize the information under the same type and form. And the last one, specifying which features are relevant to the association of the kind of thing is a job of theory. Meaning here, theory itself has to determine which characteristic and features are suitable to the relationship of the thing. In a conclusion, observation can be categorized into two, which are qualitative and quantitative observation. Observation is essential in science. Scientists use observation to collect and record data, which enables them to construct and then test hypotheses and theories.